Welcome to the Climate Change Workshop. We have a robust agenda that we're excited to dive into this morning. So we're going to keep our opening remarks short and sweet, but we want to start with some introductions. I'm Larna Cates. I direct Denver Water's Climate Adaptation Program. I'm also chair of the Water Utility Climate Alliance. We're an alliance of 12 members across the United States working on climate adaptation on behalf of the water community. And my work is primarily focused on science and research, on planning, and on policy.
All right. My name is Russ Schumacher. I work at Colorado State University up in Fort Collins at the Colorado Climate Center and serve as the Colorado State climatologist. I do research and teaching related to weather and climate, especially on the precipitation side, but then we also do a lot of work related to drought monitoring and things along those lines that we'll talk about here later this morning.
Morning, I'm Taryn Fennessy. I'm the senior state climatologist. I don't know what I am. I'm the senior climate change specialist for the state of Colorado. I'm housed within the Department of Natural Resources, and I manage our climate change program as well as our drought program. And I take the research that these fine folks do and translate it into policy. We are getting feedback. Are you guys hearing feedback when I talk? Oh, great. So it's just us it's going to annoy. That's better than annoying you. So welcome. Thank you for participating. I'm going to hand this back over to Lorna. She's going to give you a quick overview of what to expect for the morning, and then we'll dive right in.
All right, so Doug invited us to put together our agenda today. So thank you, Doug, for this opportunity to bring a robust agenda to you guys this morning. And we're all here because we care about water, right? And what we're going to learn this morning is climate change means water change, and water change is our business. Frankly, we thought that climate change was going to be the next generation's challenge, but unfortunately, it's here and now. So we need to start taking this seriously. It's potentially going to be one of the greatest challenges that we have to deal with as a community, as a nation, and as a world in the 21st century. And climate change is going to impact all facets of water. So this morning, we're going to take a dive into science, data, research, and learn about what climate change means to Colorado. We're going to learn about climate change in the context of the last several decades. We're going to learn about climate change in the context of the last several hundred years. And then we're going to do a deep dive into the extremes and better understand what types of extremes we could be dealing with and how we might start planning for them. Then we have a 2-hour lunch break, and we're going to come back together and start learning about who's doing what, how they're doing it, and why they're working on this with a series of case studies after we do an interactive exercise. We're going to end the day with a policy conversation of how climate change should be fitting into policy, how it could be fitting into policy, and how it's going to be potentially disrupting policy. And throughout the day, we're going to be thinking about where mitigation fits throughout the whole spectrum of climate adaptation and our work in adaptation. Many of you are probably familiar with the National Climate Assessment Report that came out most recently. They had economic evaluation in that report, and they estimate that we could save 70 to $80 billion in damages if we mitigate greenhouse gases instead of staying on the path we're on now. That's significant impacts to our economy, to our public health, and to our resources. Do you want to say anything else?
So I just want to echo that when we talk about climate change in Colorado, we're talking about water impacts. Regardless of what sector, and climate change has the potential to impact all facets of our economy, one of the biggest concerns that people have is water availability, water quality, changes in our precipitation patterns. And so this really hammers home to what you all deal with. And so we're going to hopefully take the science and then merge it into practice and policy, because these things have to be approached in tandem. It's not all about the science, it's not all about the policy, it's not all about the practice, it's how they fit together, and that's how we're going to be most effective in addressing it. So we're trying to give you the whole package today. I know it's going to be a long day, but if you can stick with us, I think you'll be able to really put the pieces of the puzzle together.
Great. So we're going to go ahead and get kicked off with our morning agenda. I'm going to invite Jeff Lucas, who is our first speaker, up to the stage, and we'll hear from Jeff and Russ this morning before we have a break. So folks, I think, are familiar with Jeff Lucas. He's with the Western Water Assessment. And one thing I want to note is that Colorado has one of the highest densities of climate and water scientists. So we are like sitting fat and happy with resources if you guys are interested in this and want to work with folks on this. So Jeff is one of those people, so I encourage you to try to meet him after his presentation.
Great. Okay. Thank you, Lorna. And thanks all of you for being here. This is a great opportunity for us to convene on, as Lorna and Taryn said, a critical issue that's facing all of us, regardless of our line of work related to water, and will only become more so in the coming decades. So when I was last at Water Congress 4 years ago, this was a brand new document that come out the previous fall, the Climate Change in Colorado report, which was a collaboration between CWCB, the Western Water Assessment, and then a number of researchers outside of CU and practitioners who contributed to this report covering observed trends in climate and climate changes, and then what were the implications for Colorado's water resources. So my framing for the first part of this talk is to kind of revisit that report and some of the key findings. Say, what have we learned in the last 4 years, both from our observations, what we're seeing on the ground and in the air, climate and water change as we're experiencing it going forward, and then new studies that have come out that have done more analysis of the historical trends or looking at the projections of climate going forward. So, our fundamental problem is that we need to plan for the future, but we don't know much about it. And historically, the planning paradigm was to assume that our past variability, our average, our extremes, our drought of record, would, at least in a statistical sense, repeat itself over the next 20 or 50 years, however long your planning horizon was. So the assumption of stationarity. And we now have, very good evidence, just from climate change that assumption is no longer valid. And there are other reasons to think that we should not be holding to an assumption of stationarity. But that leaves us in an even bigger bind. What is our guidance for moving forward into the future? So one of the frontline findings of the 2014 report was that Colorado had warmed by 2 degrees in the previous 30 years, and that was a period ending in 2012, which was the last year for which we had complete data. And so 2012 was that highest bar on the right-hand side. That was the warmest year in Colorado's history. And you could expect that to some degree because it was a very dry year, and drought years tend to be hotter years. They go together over time. If you look at past very warm years like 1934 and 1954, those were extreme drought years. So what's happened in the 6 years since the report, the last data in the report, and that's what I've got shaded in red, those 6 years you kind of snapped a little closer to the late 20th century average, and then the next 4 years, so 2015 through 2018, have all been in the top 8 warmest years on record. And I think what's really significant is that 2015 to 2017 all had near average to slightly above average statewide precipitation. So we've got normal years precipitation-wise that have near record temperatures. So I think that is really, even more so than 2012, the record hottest year for Colorado. 2015, 2016, 2017, non-drought years that were extremely hot. That is really, in my mind, the confirmation of this climate change signal. And so I'm more confident than I was 4 years ago in attributing most of that 2-degree warming to anthropogenic climate change, kind of our global changes coming home to roost here in Colorado. And this is significant because warmer means drier. The atmosphere exerts a heavy tax on our precipitation. If we look statewide at our water budget, the most salient fact is that over 80% of the precipitation that falls as rain and snow across the state goes back up into the atmosphere as evapotranspiration. Now, if you're just isolating our mountain headwaters, it's closer to 60%, even 50%. But that evapotranspiration term, what goes back up, that red arrow, is incredibly significant. We don't really feel it or experience it on a year-to-year basis. We feel and experience the variability in precipitation, but that red arrow is there in the background doing its thing year after year. It's a little bigger as a percentage in drought years, smaller in the wet years, but it's taking most of our precipitation back up, and it is largely driven by temperature. That's why we have more evaporation in summer, and the same thing happens when we have a warming trend. And so again, warmer equals drier, all else equal. When we have warming temperatures, it drives up evaporative demand, which means any water that's at the surface, whether it's in plants or snow or soils or surface water, is more likely to enter that big red arrow and leave us with less runoff. So what's going on the precipitation side? So in 2014, the report said, looking back over the last 30, 50, 100 years, we don't see statistically significant trends like we do in temperature. And I think that's still true, but I'll change my framing a little bit. What we do see is that it's slightly drier overall since 2000, and we now have had 3 extreme drought years in terms of precipitation over that about 20-year period. And I'm not ascribing this to climate change. I'd say the jury is out and tends more towards pointing to natural climate variability as the reason for this relatively dry period over the last 20 years. But it's certainly something to keep an eye on, and in combination with the warming, it creates real problems for us. So we have this snowmelt-dominated hydrology in Colorado, and the vast majority of the surface water in our streams and rivers at some point was part of this great seasonal reservoir that builds up and then melts off. You could say it fills and spills every year. And what we also see in that blue curve is that the vast majority comes off in about a 4-month period between April and July. And so for us, the 3 questions are, okay, how much precipitation do we get? We've got sort of a normal curve for seasonal precipitation in our high country. It's fairly constant through the winter, then tapers off into the summer. Snowpack builds up, hits that peak in April, and then we've got the runoff. So first, how much precipitation do we get in a given year? Second, how efficiently is that precipitation converted into your snowpack accumulation? And then from your peak snowpack, typically in April, May, how efficiently is that converted into runoff? So we got 3 questions. And the first one, precipitation, going down, I'll say lower in the past 20 years, but I'm not going to say that's a long-term trend that we necessarily expect to continue. So it's very hard to tease apart, questions related to this, efficiency in generating the snowpack and the efficiency of runoff itself from snow and precipitation, by observations alone. There's so much variability from year to year, and so we turn to hydrology models or land surface models to try to get a better sense at what's going on under the hood, the different processes, how they're interacting. And when we ask them, how sensitive is the hydrology, are the watersheds of Colorado to warming temperatures, you get somewhat of a consensus of a 3 to 4% decline in annual runoff for each 1 degree Fahrenheit of warming. And there's some outlier models that say it's closer to 2%, some say more like 4.5%, but 3 to 4% per degree Fahrenheit is kind of a consensus of those models. So how is this happening? I gave you the kind of the general sense of warmer equals drier, that evaporation term goes up as a fraction of your precipitation. More specific mechanisms are when you have warmer temperatures in fall and spring. What used to fall as snow is more likely to fall as rain. Rain is less efficiently converted to runoff than snow. You would rather have your precipitation fall as snow, build up that snowpack, and come off in a hurry. It's less likely to be part of that big red arrow going back up. When it's warmer, whatever is in the snowpack, you're more likely to have sublimation loss directly back to the atmosphere from the top of that snowpack. When you have warmer temperatures, snowmelt tends to initiate earlier. When you have earlier snowmelt at lower sun angles earlier in the spring, the snowmelt is actually slower than when it initiates in like June, when you have a big May, like May 2015, and then it all comes off in June. You'd rather have that than snowmelt initiating in February or March and then sort of dribbling along through the spring. You get less efficient runoff that way, and then dust on snow just adds to that problem by, again, initiating earlier melt. When snowmelt comes, when you have meltout, complete meltout earlier, soils are exposed, and so you get more evaporation from those soils than you would otherwise have. And then vegetation can start growing earlier on those exposed soils, and you have a longer growing season and more transpiration. So it's all sort of work together, supporting that idea warmer equals drier. So what are we seeing on the snowpack side, the top of our accumulation curve? And again, in the Climate Change Colorado report, we looked at snow accumulation or peak SWE by basin and over time, and we saw no statistically significant trends. I haven't rerun those numbers. Those might change, but certainly if you eyeball what's going on, and this is statewide April 1, so close to our statewide peak, over the last 50 years, we sure looks like a downward trend. And if you look at the last 21 years, since 1998, all but 5 of them have been below the long-term average. So we're definitely in a drier period in terms of snowpack, lower snowpacks at peak. Is it less, are we seeing less snow than we would expect given the precipitation, which has also been lower for the last 20 years? That's really hard to say. Frankly, we don't measure snowpack on a statewide basis accurately enough to really parse it out from observations alone. But I'm increasingly confident that we are seeing snowpack loss due to the warming, that it's adding on to this sort of hopefully more natural downturn we've experienced in the last 2 decades with snow. Then the really critical part for those of us in the water supply business, okay, what is coming down our streams and rivers? And here, again, in the Climate Change in Colorado report 4 years ago, we showed these time series of annual runoff for the South Platte, Arkansas, Colorado at Cameo, and the Gunnison. And we said, boy, a lot of variability. It's fairly synchronous. Storm tracks are either on or off for the whole state in a given year. And we don't see statistically significant long-term trends. I think that's probably still true, but particularly after 2018, I think we look at the last 20 years and we say, wow, we've got less water over the last 20 years in our streams and rivers. And then we have to ask, is it less than we would expect given the precipitation and snowpack? Again, hard to tease out, but increasing evidence that the answer is yes. We're starting to see that 3 to 4% of runoff decline per degree Fahrenheit warming that the models tell us to expect. There have been some high-profile papers that have come out about the whole upper Colorado River Basin suggesting that. I am supportive of their overall conclusions. We can quibble about methods because it's, again, really hard to pull this directly from the observations, which would be the best evidence. So we have to turn back to the models, which to some degree are calibrated on those observations. So, but we are seeing a consistent picture, and I think part of the recent, lower snow runoff in our streams and rivers is because of that warming. So an exercise that I did mostly for my own purposes to see if by isolating a smaller sub-basin of the upper Colorado, I could see what these papers were trying to show at the larger basin scale. I looked at just the Roaring Fork at Glenwood Springs, and using a naturalized runoff record, which of course you have to have if you want to isolate climate effects, we see 13% lower precipitation from 2000, this is through 2016, that red dashed line, versus the long-term average, while basin annual precipitation was only 3% lower. You say, well, that's a 10% difference. You actually have to more or less double that precipitation departure. So with 3% less precipitation, you would expect about 6% less runoff. So that gives us a 7% difference between what you would expect from the decreased precipitation and what we're seeing at the gauge. And that's actually a consistent picture. You say about 2 degrees of warming in the Roaring Fork over the last 20, 30 years, and we're seeing maybe 7% less runoff. Now, this is showing a consistent picture number-wise. We may be getting the right answer for the wrong reasons, because it's really hard to measure all of these terms with that precision over the basin scale. And so it's really, we're going to have to keep accumulating evidence as time goes on, but I think we're starting to see, if not a smoking gun, I don't know what to call it, a smoldering campfire, showing us there's smoke, and there's probably some fire there too, that we're seeing declines in runoff already from the warming that we've already experienced. What we're more confident about is that we're seeing shifts in runoff timing. We know that this is a more sensitive metric, or a metric of runoff that's more sensitive to warming, and we've been seeing it across the West, in Colorado by about 1 to 3 weeks if you compare the 2001 to 2010 period to the previous 50 years. So that's a pretty strong signal there, is the runoff shifting earlier. All right, so to sum up what observations and new studies from the last several years, since I was last behind the podium at Water Congress, temperatures, that significant warming continues, particularly think about 2015 to 2017, years with near average precipitation that were also near record warm. Precipitation itself slightly lower since 2000. Can't really attribute it, probably due to natural variability, but we're not entirely confident about that. Looking at the water cycle, again, climate change is water change. Lower snowpack and runoff since 2000, and runoff efficiency does appear to be declining. We're getting less bang for our buck. So the upshot is that warming is having some impact on our water cycle already, though it's a little hard to quantify, but we've got a lot more coming in the pipeline. And this is the reason. We have been, massively changing the composition of our atmosphere. We've been making sort of the thermal blanket over the Earth's surface thicker by increasing carbon dioxide, methane, CFCs, other greenhouse gases. And, as you are probably aware, carbon dioxide is now over 400 parts per million. I was reading a book the other day that was published in 1994. It had a similar graph. The top number on that graph just 25 years ago was 350. And now we have to put, pretty soon 410, 420 on our graphs. This is a huge change that we're making to a part, an aspect of the atmosphere that has tremendous significance for the global climate, and thus the climate here in Colorado. And we're seeing at the global scale, record high temperatures in 2016, 2017 came down a little bit. We don't have the latest numbers from NASA for 2018 because of the shutdown, but hopefully we'll get those soon. So how do we get that better sense of the future if stationarity is no longer a valid assumption, if we cannot assume that the last 100 years will repeat itself in an endless cycle, then where do we get some quantitative guidance? And we have global climate models, incredibly sophisticated, complex computer models that integrate all of our knowledge of the climate system and expose the gaps in our knowledge as well. And also our assumptions about the future emissions of CO2 and other greenhouse gases. So these are tools. They're not crystal balls, but they're the best tools that we have. And they were not purpose-built to help the people in this room necessarily. They're not, built for that purpose of providing guidance at the local scale to water managers and other folks trying to make decisions. But we can do the best we can to make them fit our purposes. And so this is, I think, a very telling comment from two climate modelers. And if we had observations of the future, we would obviously trust them more than the models. But unfortunately, observations of the future are not available at this time. So we do the best we can with these models and with other tools to try to give us some hazy view of what the next several decades and longer might bring us. So, major uncertainty I just alluded to is we don't know how much carbon dioxide and other greenhouse gases, GHGs, we will continue to emit as a global community into the atmosphere. And so we create these as a research community create these emissions scenarios called RCPs, representative concentration pathways. The blue one is one that's often used to represent a low to moderate emissions pathway where significant curtailment of greenhouse gas emissions are made. RCP 8.5 is a business as usual or even business as usual plus. We really stay on a very carbon intensive pathway with no real effort to mitigate greenhouse emissions. And you can see we're still at kind of a fork in the road, though frankly the recent trend over the last 20 years points us more along RCP 8.5, that higher pathway. So the other uncertainty is because of our incomplete knowledge of the climate system and thus our imperfection in expressing that knowledge in the models, the global climate models themselves. And so if you ask across the dozens of global climate models a question like how much warmer do we expect Colorado to get over the next 30 years, you will get different answers. They'll be within a range. That range will have bounds to it, but they will be different as much as twofold if we're asking about temperature change. And so we kind of need to consider, think of these as a bunch of experts in a room, and we want to more or less get their consensus of the models rather than trying to anoint one model as the best model or a group of models as the better models and only listening to a subset. It's still useful to ask the whole group and get sort of the group response from the models. And because we have these uncertainties, we use multiple emission scenarios. Modeling groups around the world have developed dozens of different global climate models. So we then have hundreds of individual climate projections or different plausible scenarios of the future climate. And this makes it very hard to grapple with, especially from a practitioner standpoint. We kind of have to just buckle down and try not to necessarily pick favorites, but really consider the whole range of the output from the models. We have this global effort that's been going on for a few decades called CMIP, Coupled Model Intercomparison Project, that tries to systematically generate those projections of the future across all of the different modeling groups around the world under consistent conditions so that we can compare them more easily from one to another. And we've had CMIP 3, there was no CMIP 4, CMIP 5 was several years ago, and the data from those sets of projections or ensembles of model projections have been used in different studies that include Colorado, some from the state, some from reclamation of the basin states. We're awaiting CMIP 6 coming out in the next couple years, but don't hang your hat on some great breakthrough coming from the next set of models. We see continuous improvement, improved resolution, improved representation of processes, improved representation of things that really matter to Colorado's climate, like El Nino, La Nina, the model topography, things like that. But we will not get a resolution to our big question mark about the future from CMIP 6. We'll maybe just get a little more refinement on some key questions that we have, but not the big question. What is the future going to bring us in terms of water supply? So again, looking across all of the projections available to us from the models, and this is CMIP 5 data, so the latest set of projections, we do see a uniformity or consistency. All of the projections, all of the models are calling for more warming for Colorado. Regardless of the emissions scenario, regardless of how the model represents climate, they all say it's going to warm. So we can hang our hat on this. Colorado will continue to get warmer by several degrees through mid-century and beyond, and the question is really by how much. Though if we wait long enough, we stay on that high emissions track, we will hit all of those degree thresholds eventually if we don't get emissions in check. So we are taking Colorado's climate out of the historical envelope and into territory in terms of temperature we haven't seen before. So again, thinking that warmer equals drier, under 5 degrees of warming relative to a late 20th century baseline, we would expect, because of that evaporation term going up, that arrow getting bigger, that our runoff declines to 80 to 85% of normal. That's in an average precipitation year. So we're kind of moving towards a state of quasi-drought, even in the normal precip years. precipitation itself, it's kind of like the historical record and the most recent trends. We don't really have a clear indication. The models are not in agreement of whether we will see a little more precipitation in the future, annual average over the next several decades, a little less, or about the same in Colorado. And the emissions scenario doesn't make much difference. So this is really about how the models are handling things that affect the storm tracks that either hit us or don't in Colorado. Most of the models do tend to show a little more variability from year to year than we've experienced in the past, and that's not necessarily welcome, because if we're seeing higher highs, we'll see lower lows too, and that means deeper droughts. Seasonal precipitation, there is more of a consensus that we are likely to see an uptick in winter, so midwinter, December, January, February precipitation, but probably less in summer, though that's a little more uncertain. So, we can try to make this otherwise unruly ensemble of hundreds of climate projections a little more tractable. First of all, we need to bring them to a local scale through downscaling. There are many techniques to do this. So the grid size of the GCMs is too big to really give us answers at the watershed scale that we need in Colorado. And so we have to downscale the data. Often after it's downscaled, we'll put it through a fine scale hydrologic model like the ones I showed in the slide earlier, but then you still have hundreds of traces of future hydrology to deal with. So one thing that can be useful is to distill that range from the dozens or hundreds of hydrologic traces and climate traces and develop some scenarios that kind of synthesize, kind of upper, middle, and low. And you see different efforts that have done that. The Colorado Water Plan actually incorporates a little of that, multiple scenario, small number of scenario thinking, hot and dry, repeat of historic, and then a scenario that's between hot and dry and the historic. So putting this all together, and I think this will be fairly similar to messaging I gave 4 years ago, what should we expect? What is likely to happen in our water future over the next several decades? First of all, reduced annual runoff is likely. I'm almost went for very likely. It's not certain. And if we look at the lower graph, and that shows change in runoff, running 30-year averages from about 30 different climate models. And I'm leaving it, I'm saying this is just Upper Colorado River. I mean this to be more schematic than saying this is a particular basin. But we can see that a few of the blue lines at the top of that spread, those are scenarios in which there was enough increase in precipitation to counterbalance the drying effect of the warming temperatures. In just about every other trace, though, either your precipitation has gone down or, more likely, the temperatures have gone up enough to take runoff down by themselves, regardless of what precipitation was doing. So we don't want to count on those blue lines. We might get enough extra precipitation in the future because of climate change, but I wouldn't count on it, and it looks like our future will include less runoff, particularly for southern Colorado. The models are in a little more agreement that southern Colorado, like the San Juan and Rio Grande basins, are likely to see less precipitation on an annual basis in the future. So there'll be double hit, it's likely. And then again, very confident that we will continue to see earlier runoff as the warming continues and even increases over time. So another 1 to 3 weeks earlier over the next 30 to 40 years. So not only does your peak shift, but this means that your late summer base flows kick in even earlier, and that's going to be significant for ecosystem purposes, for water quality issues, and for your direct diverters from your streams and rivers. May not be able to finish crops in this kind of scenario. And then, again, you've got higher evapotranspiration in a warmer climate. This means your crops and other vegetation will need more water, assuming you still have the same crop mix and same outdoor greenery. So assuming that, the modeling that's been done for Colorado suggests that those parts of our demand term will increase from 5 to 30% by 2050, depending on the amount of warming and whether summer precipitation, which of course is really important in modulating our demand, both ag and outdoor urban use, whether that goes down or not. We don't say much in the 2014 report at all about water quality, but I think we can say now that more challenges are likely for water quality issues. Warmer temperatures mean that chemical reactions and biological processes occur faster, including the ones that create water quality issues. We're expecting a future with more wildfire in Colorado. So more wildfire burned area means more erosion and sedimentation. And then again, as the peak of runoff shifts earlier, lower late summer flows, and so less dilution of pollutants in the late summer and fall. Also, and this will be hit on in a later presentation by Kelly Mahoney and Bill McCormick, we're expecting an increase in heavy and extreme precipitation events. And this is the flip side of that warmer climate being able to hold more moisture. Most of the time, we do not have a saturated atmosphere above us in Colorado, and so the atmosphere will want to pull free water out of soil, water, plants on the surface. When we do have those weather patterns that bring a saturated atmosphere, that warmer saturated atmosphere can hold more water, and so we can get bigger precip events out of the same weather pattern. I put 2013 up there, what happened on the Front Range, not to say that was climate change, but it is very plausible that climate change added something on the top by making a warmer air mass that was able to hold more moisture than, say, 30 or 50 years ago. And so, for example, projections, sort of the median projection from the climate models, is that what had been a 1 in 5 year precipitation event for Colorado, the kind that tends to fill our urban drainage systems, becomes a 1 in 3 year event by mid-century. So to summarize across extreme events in Colorado, heat waves, have extraordinary confidence about. As all temperatures get warmer across the year, we will see more and longer and more intense heat waves. Drought, no matter how you measure it, and wildfires are very likely to increase as temperatures warm and the surface is dried out. Extreme precipitation is likely to increase. Things like tornadoes, windstorms, and hailstorms, we don't have much clarity about how those will change. And then cold waves are what's happening in the Midwest this week, notwithstanding. Cold waves in Colorado extremely likely to decrease in frequency over time. So one thing I want to, as I'm kind of rounding down, I want to say, we tend to look at climate change and output from the climate models in terms of average change for like a 2050 centered period. And what we have to remember, of course, is that our future will have some change driven by the things I've talked about, warming and maybe some precipitation change, changes in runoff efficiency. But it'll be a combination of that year-to-year variability, decadal variability, and an overall change forced by greenhouse gases. And these are two projections for the Colorado River at Lee's Ferry. And kind of at first glance, they look fairly similar. They show a decline into mid-century and then kind of hold that decline in flows to late century. But if you look at the lighter blue line, it has some much deeper droughts. And so it's those details. The devil will be in the details, not in the average change as much as do we get, a 3-year or 4-year low flow or drought that's, much worse than the historic drought of record for our Front Range systems. And also that lighter blue trace doesn't have the peaks above 20 million acre feet that you see in the other trace. And so you wouldn't fill the big reservoirs in the Colorado system as well. So back to our problem. Have I solved this problem in 40 minutes? No, of course not. Will we solve it with the next generation of climate models? No, we won't. In 30 years, we're still going to be grappling with this problem. But I think we'll have we can shade that lower part, unfortunately, of that polygon a little more than the upper part. And that's where our vulnerability lies. And so we want to hedge towards that anyway, just to make sure we are safe and providing robust water supplies for urban and agricultural users. We still face this general problem, but hopefully a little more guidance about what future to expect. And really, you know, what I could tell you from the climate science community can only go so far. And there are real limits to what we can say about the future with a climate model. So really, I have to turn it back to all of you in the room and say, what's equally, if not more important, is to really understand the limits, the vulnerabilities, the sensitivities of your system. How your system, whether we're talking about your agricultural yields or municipal water supply, your system's performance in past droughts or other stressful events, what you've experienced over the last 20, 30, 50 years or longer. And then to the extent that you can model or estimate or capture your system's likely performance under stresses not previously experienced. Okay, how do you create those stresses or represent them? Yeah, you can pull things from the climate models. You can pull things from paleohydrology, as JJ will talk about later. Or you could just take your observed record and shrink it. Just add a 20% decrease to the observed flows and ask, okay, how would my system perform? Or take your drought of record and shrink that a bit. You know, these are all valuable exercises. Anything to get you out of that box of your observed history, which is going to be inadequate going forward. So with that, I thank you very much for your attention, and we might have time for a question or two. Okay. Wait for the mic.
This is the workout part.
Yeah. Hey, John.
John Courier. Hey, I got a simple question that I thought I'd do the math on, but I think you've probably done the math, that I think helps put this whole situation in context. And that's, for every degree of global temperature increase, what's the additional water holding volume in the atmosphere?
Right.
You know, so we can just say, hey, we're taking this much out of the earth, putting it in the atmosphere, because I think that really,
right,
at least for me, kind of frames
so,
the issue.
So there, thanks for the question. And there is a well-known factor, you could say, it's called the Clausius-Clapeyron relation or equation that relates, how much water can be held in the atmosphere according to temperature. And it's an exponential function. So it goes up by 4% for every degree Fahrenheit, or about 6.5 to 7% for every degree Celsius. And that works out globally, it works out on the regional scale, and that's fairly equivalent to what I said is our runoff decrease too. So it's all tied to that idea of the warmer atmosphere holding more moisture. So 4% more moisture is held for every degree Fahrenheit, and that is a well-known physical relationship, and it will come up again in Bill and Kelly's talk later. Any other?
It's all good. I didn't run this morning.
Thanks, Taryn.
Charlie Spielman, Rio Grande Basin Roundtable.
Charlie, thanks.
You may choose not to answer this question. I won't hit you. What's your best guess of what would happen if we started doing heavy, in all the basins, started doing heavy wintertime cloud seeding?
Ooh, cloud seeding. Well, there's a lot of cloud seeding already. So I think you're saying if we really did it more systematically so that every range, every mountain range, every basin, sub-basin was covered. I don't know. I'm actually going to have to grapple with that literature, especially the new studies that have come out from the University of Wyoming and elsewhere over the last several years. I think we maybe have a little increasing evidence that there's a small bump, but only in certain storms, is I think with the take-home from the recent University of Wyoming work. The proponents of cloud seeding like to say 5 to 10% increase, and I can't validate that. It's so hard from observations to get a control and an experiment to say, yeah, we're going to get this much. If it's even a few percent, it's still pretty cheap water. Can I, as a scientist, say that's a good use of public monies? I don't know. I really couldn't tell you, but I think there's going to be more pressure to cloud seed in the future if runoff continues to decline. I'll say that.
darn chair's get in the way of my run.
I'm Ryan Van Pelt with the City of Loveland. I'm a water resource engineer there. And one question I had is we're revising our raw water master plan and just kind of trying to factor in climate change. We saw it a lot this last year on the Big Thompson with the hydrograph peaking about 3 weeks earlier than normal and struggling to keep our parks and rec and our golf courses green into the fall. You mentioned like 20% just kind of as a throw-out factor, but are there any better ideas? Like what if you took since 2000 and just put a higher weighting factor on the last 18 years versus the previous 50 years or so? Is that something you guys have considered?
Sure, and in fact, Bureau of Reclamation has just recently started doing that for the Colorado River. Instead of using the whole observed hydrology back to 1906 and then kind of running that forward, resampling from that distribution of flows, they're doing what they call the stress test hydrology, which is just 1988 to 2016, I think at this point. They don't have the last 2 years yet. And assuming those flows will repeat themselves. And of course, that's a much drier hydrology. So I think that's a very reasonable thing, is that will also incorporate a period of more warming, warmer temperatures than in, prior to, say, the 1980s. So if you use the last 20 years and kind of repeat them, I think that would be a good system test.
Okay, thank you for
Great. Thanks, everybody. And thanks so much, Jeff, for your thoughts and your comments. That was a fantastic presentation. Let's go ahead and give Jeff a round of applause. And up next, we have Russ putting what we just heard into the context of the last 20 years.
Yeah, thanks. So I'm going to probably repeat some of the same things that Jeff said because they're sort of core to this whole issue, but then really hone in on some of the details of what we've seen in the last 25 years. Also, just it came to mind in the question about cloud seeding. I think in those years that are sort of close to normal, maybe a little below normal, it gives you a bit of that bump back towards normal. But a year like last winter, when there's no storms, the cloud seeding isn't going to do anything, and so those really bad years, it's not going to help much. And I think that's sort of the challenge that we're left with. So let's just take a walk through temperature across Colorado. So this is the same data that Jeff was just showing, but sort of in a maybe get a little bit of a picture. And so this is the temperature with respect to the 20th century average, sort of looping over time that we see here. And of course, year to year, we see, cold years, warm years, cold decades, warm decades. But as we get to the end, those blue bars sort of disappear on there. We haven't seen a year that across Colorado that was cooler than the 20th century average since the early 1990s. So we've seen this period of the last 25 years or so being just consistently warmer than what had been the case previously, and this is consistent with the global trends that we see. And if we look kind of at this, maybe just the graph here at the end, the 2018 value there, again, because of the shutdown, we don't have the final numbers through 2018, but it's going to fit in, it's going to be somewhere in the top 10 or 12 warmest years on record for our state. And if we look at those, if we include that and look at the 12 warmest years on record, we've seen 9 of them happen since 2000. And this is not the sort of thing that you would expect to occur just as a result of chance or just a sort of randomly selected warm period. These are pretty robust values that we see with these kind of continued warmer temperatures across the state. Now, as Jeff alluded to, it's a lot more complicated with precipitation. The variation from year to year is huge. The variation from one end of the state to the other can be huge. But we see those periods in the last 20 years or so. We see those brown bars at the bottom being the very, very dry years, and we see 3 of those very, very dry years within since 2000 or so, with the 3 big droughts of 2002 and 2012 and the ongoing drought here in 2018. And so we'll take a closer look at those, but also kind of try to connect that with with what was where those fit back going back to farther in the past of at least what we know of the history of precipitation here in Colorado. So one thing we know, of course, is that the weather in a given week or a given month or even a given year is only, it's not really necessarily representative of the climate. This is a graph, just this from Fort Collins, but you could plot any location in the state and look at something like this. And so each little colored bar in the background there is the monthly precipitation from any particular year. And then the thick black line is the monthly average, right? So in Fort Collins, our wettest month is May, and so the spring is really key, and you can kind of see that. But in any given year, the wettest month might be September or October or February or March, and you may get no precipitation in the spring. And so this year-to-year variability it makes it challenging to pick out signals, especially in precipitation, because that year-to-year variability is so large. But this is sort of the challenge that we're all trying to address here: is are there any trends that we can detect, and what can we use those sort of physical principles that Jeff talked about to see whether we're finding any trends in here. And so the integrator of a lot of these issues, right, of temperature and precipitation and so forth that we're interested in, can often be represented as what we look at with drought. And so this is a history, not nearly as long of a history of all the observations that we have. This only goes back to about 2000, when the National U.S. Drought Monitor was first established. There was a realization that the country needed a way to keep track of drought conditions across the country, and the monitoring and the way that this is put together has evolved a bit over time. But this is a useful sort of illustration of the drought conditions over the last 20 years or so here in Colorado. And so basically what this shows is a fraction. So up at the top is 100%, and at the bottom is 0%, and it's the fraction of the state that is in each of these categories of drought that we're used to looking at on the U.S. Drought Monitor. So going from D0, which is not actually drought, just maybe pre-drought, abnormally dry, up to the D4 exceptional drought category, which is the sort of thing you might expect in a given location to occur once every 25 or 50 years or something along those lines. And so you see through this period of the U.S. Drought Monitor, you see these three big droughts captured that we've had in the last 20 years: the 2002 into 2003 time period, and then the 2012 into 2013, and then the ongoing drought that you can see over on the far right-hand side, and we have the question mark of where this will go now over the rest of the winter. But what also shows up here is through this 20-year period, you almost always have some part of the state in drought, or at least in these abnormally dry conditions. And this is just sort of a regular feature of our climate, where in our state, where part of the state is likely to be dry and another part is wet. But it's these sort of big things that stand out, where those red and maroon bars make it almost all the way up to the top, that feature are the things that stand out and that we need to worry a lot about when we have almost a statewide dry condition. So if we zoom in, here's the sort of zoom in on the current and ongoing drought in Colorado. You can see it ramped up, especially last fall into last winter, and in that period of November, December, January, where there was essentially no snow especially in the southern mountains. And it very quickly ramped up into this pretty serious situation that still persists. You see a little bit of a downward tick on those lines near the end. We've had some good storms recently. We'll come back to that at the end, but it remains to be seen sort of how quickly we can do away with these ongoing drought conditions. So let's take a look at kind of the similarities and differences between these three big droughts that we had since 2000, and also you'll see through here sort of the evolution of how much more of a sort of fine scale analysis we can do with the U.S. Drought Monitor than was even the case. So here's 2002, and it's a very ugly looking map here, where the entire state was in the D3, at least the D3 drought condition, and the western third of the state or so was in the D4 exceptional drought condition. So this is what made the 2002 drought really stand out, as it was statewide. There were really no areas that were spared from this. So this map is from July of 2002. This drought, of course, persisted well into 2003. And if we look at precipitation across the state, this is for the water year of 2002. You can see why the whole state was looking so bad, is that it was everywhere in the state was much below normal for precipitation, and broad swaths of the state were their record driest. So this was the drought, I think, at the time that sort of people figured was, going to be the drought of record for probably for a long time. But as we've seen, that these serious droughts have come back pretty quickly over the last decade as well. So if we look at the 2012 into 2013 drought, this is partly, you can see the resolution of these maps is getting better because we have more data and kind of a better sense of what was going on. But you also see that, again, this was pretty much a statewide drought where you had D2 conditions everywhere. Everywhere, the eastern half of the state was all in the D3, and then the D4 sort of in the far eastern third of the state. And again, looking at precipitation, it was there weren't that many places that were seeing record dry conditions during this one, but very large areas that were seeing way below normal precipitation in this 2012 to 2013 period. In some parts of the state, this drought got wiped out pretty quickly by the September flood in 2013, and we'll take a closer look at that later. But you can see what the precipitation pattern looked like there. Now, our current ongoing drought. So this was the Drought Monitor map back at the beginning of the new water year, early October. And what you see is compared to some of those past droughts, 2002 and 2012, this one wasn't completely statewide. The northeast corner of the state actually did okay last summer, especially with thunderstorms and rainfall. Unfortunately, they had a lot of hailstorms as well, which doesn't help. But the precipitation there was reasonably okay. But what makes this one stand out was just how awful the conditions were in the southwest corner of the state, where it was near record or record low precipitation in a lot of areas there, and as we'll see, it was extremely hot as well in western Colorado that exacerbated these conditions. And so if we look at the precipitation for the water year that ended at the end of September, again, we see basically that Four Corners region, that southwest corner of the state, was record driest everywhere. Again, not a statewide drought. We had parts of the state that were wetter than normal in the summer, but the intensity of that drought in southwest Colorado was really, I think, probably unprecedented for that part of the state. And again, it wasn't just the precipitation. It was because it was record dry in that area in southwest Colorado, and also record warm. And so the left graph is the same one I just showed, and the right map is the temperature with respect to average. And you can see everywhere west of the divide was record warm, or very close to that over last year. So it's, as Jeff said, warmer means drier, and if it's not raining or snowing, then that is kind of a multiplier effect there. So it was a really, really bad year for western Colorado in the water year of 2018. Okay, some of this, another way to look at this, right? It's not just the averages. Another way to look at this is some of the temperature records that were set in western Colorado from this. And there's a couple up there. The number there at Montrose, that's 78. So this is the number of 90-degree days that were observed last summer. The number at Montrose really blew our mind because it broke the old record. The average, so the red numbers are what was observed in 2018. The purple numbers is the average number of 90-degree days. Almost everywhere in the state had above average number of 90-degree days, but this was really amplified on the west slope. So at Montrose their average is 34. I think the previous record was something like 55 90-degree days, and they had 78 90-degree days, and that's a very reliable long-term station there. Grand Junction tied their record for 90-degree days, so just incredibly warm, and of course this puts a lot of stress on water resources and agriculture in that area. So another way to look at that, this is our COAGMET, the Ag Weather Network that we run out of our office. The station at Olathe, which is one of our longer-term stations, goes back to the early 90s. And this was one way of looking at this. So this is a graph just during the growing season of evaporative demand, so going from May 1st through the end of September. And these are all the different years that were observed on the graph here with the so the higher values here represent the atmosphere being thirsty, essentially, where it's warm, the humidity is low, and there's not a lot of cloudiness. So the blue line is 2018, and so for almost the entire summer, you can see the evaporative demand, the thirst of the atmosphere was way above anything that had ever been observed since the mid-90s at that location. If we look at, and this is a time series then, just another way of looking at the same data to see which years were the highest. And you can see one of those years in the early, I think it was 1994, had previously been the highest, and then the 2018, by the end of the growing season, was right up there with that. So it reflects the combination of the warm and the lack of precipitation in that area. So here now we compare, this doesn't directly include precipitation, but if we look at the precipitation there, the blue line again, 2018, basically at the bottom of the record for this station at Olathe. And then if we do the water balance, so basically the precipitation that we just saw minus this graph on the left, and you can see that blue line basically setting the record at that area for the water balance or the negative water balance. There's always a negative water balance there, right? We can't do dryland farming in western Colorado. There's just not enough precipitation to do that, but the amount of irrigation that would be needed in a year like 2018 was very, very large compared to what we expect to see in that area. So that's clearly one effect on water resources. Another issue that Jeff talked a good bit about, so I won't spend a lot of time on here, but is again the issue of evaporation and reduction of stream flow and reservoir storage. So this is a now somewhat famous, I guess, figure in this world, looking at from Brad Udall, looking at the reservoir storage at the top in Meade and Powell. So you can see that the filling of both of those reservoirs and then the big decline since about 2000 or so, and the flows in the Colorado River decreasing. But the precipitation over that period, we've had some very dry years, but sort of on average is not all that unusual. But what is unusual is the temperature. It's been very, very warm over this period. And so they, in this paper, they refer to this as the hot drought of the 2000s, in that the precipitation is sort of, again, there's some dry years, but it falls within the historical record. But the combination of some of those dry years with this much warmer time period that we've already been talking about reduces the stream flow and then, of course, evaporates out of the reservoirs as well. And this was also here in Colorado illustrated quite dramatically in this past year. So this is a graph that we make to kind of keep tabs on reservoir levels in Colorado. So this is Blue Mesa Reservoir, the largest in Colorado, in southwestern Colorado. And that black line represents the current data. And you can see at last summer it just plummeted. Went into last summer pretty good, but with those warm, dry conditions, just plummeted down, basically outside of what had ever been observed in terms of the level in Blue Mesa, and continues to be at its lowest place in the record, going back to the mid 80s when it was first developed. Okay, so I'll kind of wrap up here with this graph and a couple of current images. So this is one we kind of like to look at in the Climate Center. Going back, and it's one way to try and represent some of these past droughts or the precipitation deficits in past droughts going back to the late 1800s. And so this is basically the fraction of Colorado that's in drought. Drought is kind of hard to define, but this is one way to look at it in terms of the standardized precipitation index on very long time scales. So you can see these most recent droughts. The 2018 one hasn't been added in here yet, but you can see 2002, 2012, and then some of the other notable ones in the 70s and in the 30s. And one thing that stands out to me here is if you look at those two on the far right, the more recent ones, they're actually pretty short in duration with respect to some of these back in the 30s that would go on for five years or so. These we've, for whatever reason, been able to at least alleviate somewhat in the meantime, but I think this is something we have to be prepared for. There's a historical record of these much longer term dry periods, and something intense like we saw this last winter and last summer. If that sort of situation persists for multiple years, like we've seen in the past record, we'll be in a much worse position, I think, than what we had seen. Okay, real quickly on floods, Kelly and Bill are gonna talk about this. The 2013 September flood, huge event, sort of off the charts in a lot of areas, especially in how much area was covered by the really heavy rainfall. We know we can get very heavy rain locally in Colorado, but this covered such a broad area. But a lot of the studies have been sort of inconclusive about whether an event like this really had much of a climate change influence. Some papers said basically the probability is unchanged or maybe even a little bit decreased, but others said, well, the likelihood maybe went up. There's physical reasons why we should expect heavier rainfall in a warmer climate, as Jeff talked about, but this is a complicated issue. So I think the jury's still a bit out on this. But this is a slide I showed at Water Congress last year. I don't know why it got flipped on its side there, but in any case, it's showing the population increase in Colorado, and especially along the Front Range, right? We know we're vulnerable to floods. We know that we may see heavier rain in the future, but this kind of combination of even the rainfall we know we can get now and 2 or 3 million additional people and urbanization and so forth is going to cause challenges, I think, going forward. I'm going to skip the snowpack trends because I'm running out of time and just show you sort of the current conditions here across the state. To give you a little bit of a positive note here at the end of the talk, we've been giving a lot of doom and gloom here this morning. At least for the time being, things are starting to look up in the statewide snowpack. So this is as of yesterday. We're above average for the state over the last couple of weeks, finally, which is a nice sign, but still deficits in southwest Colorado to go along with the very long-term deficits in precipitation in that region. The downside of it, as we showed, the reservoirs are still very, very low, and so it remains to be seen how much of those will refill during the spring snowmelt season. But that's why we continue to see this, even though we've had really good snow in the last month or so in southwest Colorado. That's why you still see this D3, D4 conditions down there, because the long-term deficits are so large with respect to storage and with respect to the other ecological damage that was done in southwest Colorado. I'll give a quick plug for our office. We are primarily involved in informing the drought monitor across the Intermountain West. We've got lots of maps on our webpage. We do webinars once a month or so that you can sign up for and look into. So to answer the question from the beginning, where do the last 25 years fit in Colorado's climate history? The temperature is basically the warmest that we've seen since records have started being collected in Colorado. In terms of drought, the lack of precipitation has been really intense, but relatively short-lived in that these intense dry periods haven't lasted for multiple years. They've been primarily 1 to 2 year sort of droughts. But because it's been warm, those intervening wet periods haven't really been enough to replenish the long-term water supply, and we haven't had sort of an off-the-charts wet year in quite some time. So this is a challenge that we have there. in terms of rainfall and flooding. I think the jury's still out in terms of a climate change effect there, but the widespread nature of that 2013 flood plus the increasing population growth and urbanization points us towards what the sorts of things we have to be worried about going forward. So I will stop there, and I don't know if we have time for questions, but if so, otherwise you can catch me in the break.
So I think we have time for one pressing question, and then we're going to take a break.
Hi, Lynn Brooks, Eagle River Water and Sanitation District. I read an article just maybe in the last month or so that said that the natural variation in the Northern Pacific Oscillation has masked the effects of climate change on the snowpack in the western United States, and that oscillation is about to switch. Is that factored into your climate models, and is that something you're looking at?
Yeah, so that was actually one of the slides I skipped over there because of time, and says it's a brand new study, and I think probably the jury's still out a little bit on the methods they used, and we need some more studies to kind of try and reproduce some of those results. But if that conclusion turns out to be true, it's a fairly scary conclusion, suggesting that basically our snowpack in these last 20 years that has been quite low on average would have actually been much lower if not for this natural variability that in the Pacific. So these kind of 20 to 30 year cycles that often go on in the oceans they're kind of represented in the climate models, but probably not well enough to really. That's an area where I would say the climate models do very well in these sort of longer term trends, but getting those kind of wiggles in the middle is still a big challenge. And so anyway, so it's not a very conclusive answer to that, but I think that study is somewhat eye-opening if kind of people are able to reproduce those results and show that, well, actually we should have had a lot even less snowfall during those years than we did, and that we got lucky in these 20 really dry years. If that turns out to be a robust result, it's not a good sign.
All right, everybody, let's go ahead and thank Russ for a great presentation. I think that last question really goes to point out there's a lot of uncertainty that we're dealing with, and really knowing our system, what our system can withstand, and why is critically important. All right, everyone, we're going to go ahead and get started on our agenda again. I wasn't joking when I said a quick short break. So I'd like to invite JJ Shrinker to the stage, or I think I said your name wrong. Shrinker. It's just because I'm short, so I'm just putting short jokes in there. So JJ is coming to us from the University of Wyoming, and she's also going to be giving a presentation tomorrow, I believe, as well. So if you can't get enough of her today, please make sure to see that. Let's go ahead and welcome JJ.
Thank you very much. Good morning. Thanks for coming back after the short break, and thank you for inviting an outlander to come down here to Colorado and talk about drought and water and climate variability. Here I'm going to take a little bit of a longer time perspective, even beyond hundreds of years to thousands of years. What I have here on the title slide are a couple of images from a publication that we had in 2010 that was looking at the North Platte River headwaters. This is in Creedmoor Lake in northern Colorado. We're pointing here at a former high stand of the lake. We've done some reflective ground penetrating radar profiles of this lake, and the dashed lines on the right-hand side are an indication of how low the lake has been in the past, the estimated lake surface, about 8,000 to about 5,000 years in the past. I'll come back to this in a moment. First, I want to give you an outline of where we're going. Before I do that, I want to give some acknowledgments, of course, to the graduate and undergraduate students that have helped in the climate lab at the University of Wyoming with the research, as well as other folks that I collaborate with and funders who have helped support much of the research that I'm going to be showing you today. Many of us work on this notion that the present is the key to the past, and I'll add to that that the past is also a key to the future. In terms of thinking about precipitation changes, in terms of thinking about variability, as Jeff and Russ pointed out, variability is sort of, in a way, a baseline for us, especially here in the Intermountain West. I'm enamored by variability. I love it. I'm sure water resource managers don't. But what I'm going to present today is a little bit of a middle ground here by trying to present some examples of how the atmosphere is actually operating during times of variability and during times of extremes, but also with a nod to some of the things that both Jeff and Russ talked about in terms of trends as it relates to increases in temperature. We're dealing with an arid place, the interior Intermountain West, with its variability and its extremes. We have a variety of different pieces of evidence. Today, I'm really going to focus on evidence from ground-penetrating radar data in terms of providing context for past lake-level variability. Tomorrow, I'll give some additional paleo-environmental context as it relates to sedimentary data, as it relates to pollen, and even charcoal that give us an indication of changes in landscape, changes in vegetation, changes in fire frequency, and how that relates to climate. My contributions to sort of these big picture perspectives is looking at how the climate system is actually operating. And I do that in a few different ways. I'm moving beyond here in this presentation, beyond temperature and precipitation, by incorporating a variety of different components of the atmosphere that help us understand how the atmosphere is moving, how the atmosphere is operating as it relates to dry conditions. I do that by looking at modern climate data and using those as analogs for past environmental changes that we see in a variety of different proxy data. This helps us provide some context for some of the first order processes that are working within the atmosphere that lead to some of those changes, some of those variability, some of that variability, some of those extremes. Future water resources are important to think about, and here we'll focus on the notion of trends, much as Jeff and Russ have discussed here, as it relates especially to springtime temperatures and snowmelt runoff. Here we're looking at some components of spatial distribution of precipitation. On the left-hand side, we're looking at winter versus summer dominant precipitation. Okay, this is one way of thinking about variability that occurs within the interior Intermountain West, or this area in the sort of middle of the western US, where these values are kind of low, shaded, not very dark, not the winter-dominated precipitation of the western part of California and Pacific Northwest, not the summer-dominated precipitation that we see in the western part of the Great Plains. We're in this area where you can see that there's elevational variability, but also overall spatial variability. It just so happens that we're looking at headwaters to many major river basins within that region. This is another way of looking at it here. We're looking at a temporal perspective. On the x-axis, we're looking at January, February, March, each month's contribution to the total annual precipitation. It's a ratio, if you will, in terms of thinking about precipitation. On the left-hand side, I'm showing the interior Intermountain West generically. On the right-hand side, we're looking at the Pacific Northwest, just in contrast. As previous presenters have pointed out, we have oftentimes in many parts of the interior Intermountain West, we have a peak of precipitation that occurs in May. Now, we have a dominance of precipitation at high elevations, but overall we have a peak in precipitation in May. But that May precipitation is actually really only accounting for just over 10% of the annual precipitation that we're receiving, in contrast to the heavy winter-dominated precipitation of the Pacific Northwest. In other words, if we miss our mark for a given month in terms of precipitation, a region could be in drought pretty quickly. One way to provide some context in terms of drought. Now, droughts have happened recently. As we've seen by our previous presenters, droughts have happened even in the way back past, and droughts are going to be occurring in the future. What we're trying to do is provide some perspective here. So I collaborate with a number of folks. One of the people I collaborate with is here in this dinghy in the back is Brian Schumann. Here, Brian Schumann and I are coring a lake to get some sediment cores to provide some long time period perspective on the order of thousands of years. Another piece of information, another proxy data that we use in terms of the research that we're doing is by taking ground penetrating radar data for lakes. And this is really actually kind of cool science. We've got this great ground penetrating radar machine that Brian bought with grant money that's on the order of about $60,000 for this piece of equipment that he very artfully put in a $20 Walmart inner tube. Not kidding you. This is real heavy science here. It's actually pretty cool. That ground penetrating radar, it can be dragged very slowly across the surface of the lake and provides us with information about past drought conditions from a long-term perspective that can help provide context from a water resource management perspective. Here's some results from one of the ground penetrating radar treks that we did. Here, this is for Emerald Lake in Colorado, headwaters to the Arkansas River. What we're looking at in this profile across the lake, you can see these sort of tan lines that kind of stick out into the sediment. This is the sediment down here. The lake surfaces are the blue parts of these images. Now, these sand lenses, if you will, represent previous shorelines, past shorelines. So it's an indication of, hey, the lake was lower in the past, and the lake was higher in the past. What these sand lenses do, once we take some sediment cores through these sections, we can actually use radiocarbon dating to identify the time periods in which those layers occurred in which the lake levels were considerably lower. That helps us give an identification to a condition in the past, right? Low lake level. Hey, lakes were lower in the past. That's the information that we're working on. The question is how did the lake become low? What were the conditions that led to those dry conditions, to the lowering of the lakes? That's where I come in. What I do is I actually look at modern climate data and try to identify past extreme episodes. In this case, consider here the dry conditions that occurred in, say, November of 2012, or 2012 in general. As we saw earlier, this is a very, very dry year. That's an example of a dry year with dry conditions, especially in the headwaters to the Arkansas River. So I take that particular year and use it as a select case, or as an example. Or I could take multiple years and average them together as select cases. So when I look at the modern record and I select a case that say, hey, it's dry during that point in time at that location, let's see what's going on climate-wise. So what I'm showing here are a series of maps. They're composite anomaly maps. They're looking at that particular case as it compares to a long-term average condition. The data that I'm using here is from NCEP's North American Regional Reanalysis product. It's an interesting product because it provides us with a variety of different climate processes, climate variables that are helpful for understanding some of the processes in the atmosphere that lead to certain conditions. It's also an interesting data set because it's about 35-kilometer grid scale, 35 kilometers by 35 kilometers, which is a really nice resolution from a climate analysis perspective because it also helps us focus on individual watersheds, which in the Intermountain West, because there's so much variability, it's helpful to have that sort of spatial resolution that allows us to look and sort of bore into individual river basins to see the variability that occurs spatially, let alone the variability that may occur temporally. So the variables that we're looking at here are precipitation rate at the surface in the upper left-hand corner. On the right-hand side are temperatures. Lower left is 850 specific humidity. That's essentially the specific humidity that's available in the atmosphere for some uplift processes to cause precipitation. And then on the far lower right-hand side are the height levels at the 500 millibar level are halfway up in the atmosphere. It's a good indication of the location of where you might find a ridge or a trough that might influence atmospheric motion or the delivery of moisture in particular. So in terms of putting these pieces together of what the atmosphere may have looked like in this analog of 2012 for past droughts that occurred based on the sedimentary record from our ground penetrating radar, this is an example. Now granted, there may be a number of ways in which drought can occur, but here we're looking at a potential example that we have seen reproduced multiple times as it relates to different droughts in different parts of the interior Intermountain West. And there are a number of components here that are important to consider. In particular, in the lower right-hand side, we see these, this big blob of red here in the central part of North America. That's an indication of higher than normal atmospheric heights, or an indication of sort of persistent atmospheric ridge conditions. And those persistent atmospheric ridge conditions have a general flow of air that is clockwise in nature. So if that general flow of air is clockwise in nature, essentially what's happening is that flow of air is delivering drier than normal atmospheric air into the region. So essentially it's blocking, if you will, moisture from the Gulf of Mexico, also potentially blocking moist air from the Pacific. So it's enhancing those dry conditions. With those enhanced dry conditions, we see an increase in temperature. Less precipitation at the surface leads to an increase in temperatures at the surface, which helps to sort of provide a positive feedback loop in terms of those dry conditions at the surface. Now back to Creedmoor Lake in the North Platte Basin. This is an interesting story here, and here I want to shift from the notion of atmospheric moisture and atmospheric movement to the notion of trends. In terms of the Platte River, especially the North Platte River headwaters, this is an area that is 100% allocated, like much of our water in the West. In particular, it's allocated between Colorado, Wyoming, and Nebraska. In terms of this particular basin, and here I have it outlined on the right-hand side, Creedmoor Lake is part of the headwaters. There's no impoundments above Creedmoor Lake, so we get a sense of the general conditions that are occurring within that lake based on the paleohydrologic record in terms of the geophysical data. We also have information historically in terms of the temperature and precipitation that we have from NCDC data. Now, here I'm going to talk about temperature trends. So the notion here is to sort of ask, what are some of the conditions, or how might recent climate change affect water supply? And to me, this is actually a really interesting story, because on the one hand, what I showed you with the Arkansas River headwater basin are some of the climate processes that can lead to drought. Here I'm going to talk about the trends. In terms of thinking about temperature for the North Platte Basin, based on climate from NCDC, we're showing annual conditions in the dark gray, and then the black line shows spring or March, April, May temperatures. You can see there's year-to-year variability in terms of those temperatures, just like there's year-to-year variability in terms of precipitation. But in terms of temperature, there is an identifiable trend, and a statistically significant one at that. Temperatures are increasing annually. They're actually increasing every year, every season of the year. But the temperatures are increasing at their fastest rate. And in fact, temperatures are increasing at about 1.5 times the annual rate. So springtime temperatures are increasing even faster. So the fastest temperature increase is occurring during spring, which therefore is going to impact our snowmelt runoff. So then we look at winter precipitation. And much like we saw with our previous presenters, winter precipitation, while there may be a decline, it may not necessarily be a very robust or statistically significant decrease in temperature, although the decrease in temperature in winter does seem to be significant, especially in this particular headwater region. Combining these notions of rates of change in terms of increases in temperature and changes in wintertime precipitation, Here we're linking it with stream flow. In this particular case, we're considering the trend, the advance of peak runoff, on the order of about 10 and a half days over the period of record since the early 1900s. That's equivalent to 4.75 days for every 1 degree increase in March, April, May temperatures. In other words, this is an identifiable quantitative value. For every increased degree in CWC, we have X number of days earlier onset of spring snowmelt. And that's something that might be able to be helpful from a water resource management perspective. So the notion of the increase in trends in temperature are valuable for helping to consider what that means from a drought perspective. While we may not be able to say increases in temperature are going to mean this amount of change in precipitation, we can say that increases in temperature mean, hey, that snowmelt's going to run off considerably earlier. When it runs off considerably earlier, that can lead to drought. Here are some images on the left-hand side for historical droughts. On the right-hand column are future droughts. What's interesting about this particular study is in both of these cases on the right-hand column, no significant changes in precipitation, but an increase in temperature is weighted in terms of future projections of drought. We've looked at these projections and we've considered what's happened recently by thinking about snowmelt and the role of atmospheric circulation on snowmelt. And this is a recent paper from the Journal of American Water Resources Association that came out to identify high pressure, consistent high pressure during periods of early snowmelt runoff. We've used this information to actually provide data for our water resource managers in Wyoming by way of story maps to identify, hey, these are areas that have had early onset of spring snowmelt as a result of the increasing trends in temperature. And those are going to be areas that may be vulnerable to drought as it relates to late season flow. So in summary, I want to provide you some perspective that, hey, the past and the present and the future includes variability. I love variability, embrace it. It also includes looking forward into the future, increasing trends as it relates to temperature, which definitely has an impact in terms of our hydrology, and the paleohydrologic variability that we can see ties in from a climatic perspective with what we see in terms of modern drought and what we're moving forward to see in terms of rising temperatures and those trends and the increases in or the decreases in water availability that we're likely to see. So with that, if we've got time for questions, I'm happy to answer any.
We do have time for questions. Are there any questions for JJ? We have a runner. She's ready. All right. Well, we'll go ahead and move on to our next presentation. Thank you so much,
Thank
JJ.
you.
That was fantastic. Okay, so up next we have Kelly Mahoney and Bill McCormick. I think Kelly maybe stepped out for a second because we are running a minute and a half early. Just kidding, we're running 2 minutes early. So we'll give her just a minute. Is she starting?
No, I'm starting.
Oh, you are?
Yeah.
Oh, great. Oh, never mind. We're going to go ahead and turn it over to Bill, and Kelly will join him on the stage.
Yeah, she will. Here she comes. I'm here to talk about our regional extreme precipitation study and how we fit climate change into that. So I wanted to just go briefly over a little bit about the study itself and then Kelly will come up and talk a little bit about the climate change aspects, and then I'll finish up with how we're applying that to the rules. So, our study was a pretty ambitious study. We needed to create updated tools and procedures for estimating extreme rainfall for Colorado. We joined forces with New Mexico to do that. And one of the main reasons was for about the last 30 years, there's been questions in Colorado about the validity of the methods that we've been using. And so these lower italicized things are from some researchers from the Bureau, and they concluded in 2011 that the methods were, as applied to the HMRs, which is the tools that we used, were outdated and static. So we had recognized that in the state, and we set about trying to fix that. We had a pretty ambitious project. We had done this once before, and it didn't come to fruition, so the second time we wanted to make sure we got it right. So we had a very robust board of consultants on this. The long column on the left up there is all the federal agencies that are involved in dam safety in the nation, basically. We had on our review board. Colorado and New Mexico headed it. It was funded by CWCB and a couple other agencies, New Mexico, Western Water Assessment. We have 3 main tasks in the study to really advance the state of the science, which we'll talk about those briefly. And we also invited all the some of the significant dam owners in the state to participate in the study, come and watch what we were doing as we did it, because we knew we were going to turn this into rules that we were going to use, and we wanted them to know everything that went into the study itself. So the first task of the study was this deterministic PMP method, that's the same way that we've been doing it for the past 30 plus years. And this is basically to answer the question, how much can it rain? So they estimate the rain in areas, and they use historical storms that have happened. They move those into locations of interest and see, could it have been worse? They look at the moisture and the terrain effects and other things to see, to maximize the storms and create new values that we can use. But these don't talk anything about the likelihood of how, what's the annual exceedance probability of that storm occurring. They just talk about this happened before, it may have been worse, it could happen again. So that was one part of the study. Since we wanted to, and the advances that we made in this part of the study was we used 40 years of newer storms. So we had the old methods kind of stopped. The storms that we used stopped in about 1976. So we went all the way up to 2016 with our storms, included the September 2013 storm in there. We have more sophisticated methods to reproduce the storms for the analysis. We have improved dew point data, climatology data. We have more objective transposition limits, which is how you move a storm from where it happened to where it could occur in your area of interest. And then we use more sophisticated GIS tools to do that. So we also applied some new storm analysis to some old storms, including advancements in dynamical modeling, which we'll talk about as well. So the second task was the precipitation frequency analysis task, and the Bureau and the Corps of Engineers had been doing this kind of analysis for their portfolio of dams, and we wanted to apply those same techniques to the state of Colorado and New Mexico. And this is where it also takes storm data, but in this case, it's not the actual storms themselves, it's the records of the storms at climate stations throughout the area of interest. And we need to be able to extend the current NOAA Atlas products do this as well, but they only go out to 1,000 years. And for extreme precipitation for dam design, we really needed to go out to beyond that, out to 1 million years or even 10 million years, 10 to the minus 6 and 10 to the minus 7. And this would, we would use that in our new tools, and it would also give us some perspective on what our deterministic PMP, what the likelihood of those numbers we were getting. So we can look at the two numbers that are calculated independently and get some confidence in what we're using. The methods that we used in our study were advances over the NOAA Atlas estimates and their procedures. We had more precipitation station data. We typed the storm, so they did a sophisticated statistical analysis using this data to type the storm so that when they did the statistics of each storm. It was a more valid statistical analysis. They looked at seasonality, like we've talked about before, moment statistics and stochastic analysis, and we looked at watershed areas as well. And then we looked at the temporal distributions from the statistically generated synthetic temporal distributions to see how the rainfall actually lands on the ground. And then one of the more exciting things we did is we included dynamic modeling methods in this study. This had not been done before, and it really seems to be the future of weather prediction models is dynamic analysis. So we are hoping that in our study this is kind of a link from the old deterministic methods to the newer methods, and Kelly will talk a little bit about this. But we use these methods, we couldn't use them by themselves for our needs, but they were able to fill gaps in data gaps within both the task 1 and 2 methods. They helped with spatial pattern analysis. They looked at the differences between rain and snow, which some of the gauge data didn't separate that out in the locations at higher elevations. And they were able to look at historical storm analysis to help define some of those older storms that were used in the analysis. As I said before, we had a lot of people on our review board. This is a picture of our first workshop that we had. Lots of really smart people in the room. And one of the things that we hadn't thought of when we were scoping the project was anything about climate change. So we had a researcher from NOAA on the phone who's in charge of the NOAA Atlas 14 program, and she was on the phone and said to the whole group, have you guys considered climate change in your study? And really that was the first time that it came up in the study, and we said, well, no, we hadn't, but the Bureau folks that were there and the Corps folks that were there said, yeah, we're starting to do that. And so we set about trying to figure out how to add that to our project that had already been scoped and contracted and everything else. And that was when we remembered back 2 years before, we had worked with Jeff Lucas and Kelly a little bit with the Western Water Assessment, and they had heard what we were trying to do, and they said, well, you know, Jeff put together a scope for this Project 6 risk assessment. It was a broadly defined scope of work that included DWR and also some of the contract folks that we were going to work with. And basically the project scope said, how can state-of-the-art science on extreme precipitation and flood events be effectively translated and applied for decision-making support? So long story short, we decided in talks with Kelly and Jeff that we could use this scope of work and the funds that Western Water Assessment had pulled together to try to complete that climate change part of our study so that we could include that in that. So now I'll turn it over to Kelly, and she'll talk a little bit about how we went about that.
All right, thank you, Bill, for setting things up, and for all the previous speakers, really, for laying the foundation here. So again, my name's Kelly Mahoney. I work at NOAA up the road at the Earth Systems Research Lab. And I'm really glad that the government reopened so I could join you here today. So just to recap, you know, why we dove into this, Bill just set the stage for the project at large. But basically, you know, PMP, how hard can the atmosphere rain? Everything you've heard today points to the fact that the climate is changing in ways that's probably going to impact the way that the atmosphere can produce a lot of precipitation. As it stands, however, the World Meteorological Organization, sort of the governing body that says how PMP should be done, doesn't call for the explicit inclusion of climate change. So that's sort of the current state of things there. However, again, we've been hearing today, and we all know there's plenty of theory, there's plenty of observations, and just a really growing body of research that is pointing to how the atmosphere is changing storm environments in ways that could affect the upper bound on precipitation. So there are also plenty of practitioners and researchers worldwide that are looking at new and improved ways at doing PMP or estimating maximum precipitation potentials. And, you know, again, just to recap where Bill left off, given Bill's vision for letting the Colorado and New Mexico project serve as a role model for future studies, we felt it was important to look into this. You know, how can climate change be affecting PMP and the way that we've considered it up to this point? So we went into it, Jeff, Lucas, and I, and we said, okay, not a whole lot of funding here, but let's see what we can do. What's the state of the science on this? We went into it and said, well, we've got about enough funding for about a postdoc's 1 month time. Just give us an annotated bibliography. What does climate change tell us about how hard the atmosphere can rain? And after a month of the postdoc's time, we got a whole lot of information back, and it was anything but clear. It was clear there was a lot to chew on and a lot to wrap your head around, but we realized we had our work cut out for us. So staring at all those, you know, the growing stack of references, we also reached out to all of the study participants, and Bill mentioned, you know, this ranges from dam owners to experts in the research field and everything in between. We reached out and said, you know, how important do you guys think this is? And I would say that overwhelmingly the survey results that we got back, and we asked the question in a number of ways, overwhelmingly we were surprised at how much interest there was. There was very little agreement in how this should be done, and how you would incorporate climate change into this process, but there was more traction in the community than we anticipated. So that, in addition to input from our project review board, in particular, we had a couple of really, you know, world-class experts in this. Ken Kunkel, he's the lead author of the 4th National Climate Assessment. John Nielsen Gammon is the Texas state climatologist and a world-renowned expert in, you know, extreme precipitation, and others on the board. We were able to engage in really focused conversations and additional research even on the side. So point being, this grew from a 1 month annotated bibliography into, you know, a more substantial chapter in the final report of this project. And so what I'm going to spend the next few minutes doing is just walking you through the high points of the executive summary, and then leave it with a set of fairly broad brush recommendations that we made, and then I'll hand it back over to Bill and he'll let you know what he's doing with those. So starting out, again, the current established practice in PMP does not consider climate change. So we suspect, again, knowing what we do about warming and its connection to precipitation, we suspect that there's room to do something about this. So what we do know, and as Jeff and others have shown very clearly this morning, is there is a solid chain of evidence that anthropogenic climate change is going to be, is behind, you know, all our observed recent warming. And the model projections obviously continue this to some degree as in the coming decades. You've already seen this a couple of times today, but again, here's the warming. We know it's there, we know it's happening, and we know it's projected to go up. So going back to some of the questions and discussion that we had, how does this connect to precipitation? And we're just going to use the relationship between temperature and moisture holding capacity of the atmosphere. So Jeff already alluded to this, you know, somewhat fundamental thermodynamic relationship. The warmer the air is, the greater its moisture holding capacity. And we see this in a range. These are, again, a similar set of the CMIP-5 climate projections, the models according to the 2 different RCP pathways. And really, no matter how you slice it, averaged over Colorado, the maximum precipitable water, so just something that we use to say how much moisture the atmosphere can hold, it goes up and up and up. You know, again, regardless of your projected greenhouse gas contribution. So we know that one of the main ingredients in getting extreme precipitation is projected to increase, and this is closely tied, or it is inherently tied to the increase in projected temperatures, which we feel pretty confident about. So following this relationship, the warmer atmosphere will give us higher moisture values on a global basis, and we really do increasingly understand this on regional and local scales as well. So I'll just say here that climate change is definitely expected to affect other aspects of extreme precipitation. For example, the inner storm dynamics of flood-producing systems, the intensity of precipitation, the duration over which it can last, and things like precipitation efficiency in the phase, so rain, snow, hail, and so on. But the current science, we do know a fair bit about those, but we understand less about how they interact with each other. And so for the purpose of PMP, which is already really broken down fundamentally into different ingredients, we can actually use some of those simplifications here to say, we're going to hang our hats on the most robust signature, the connection between temperature and moisture holding capacity, because PMP already asks the question, how much moisture can the atmosphere hold? And assuming it's at that maximum capacity, what happens when you kind of wring that out? So also want to mention that we looked at many studies that have tried to investigate very specifically how climate change will affect PMP, and there are a slew of methods out there. This table summarizes just a few of these studies, and I'll say that the methods are all across the map, statistical, dynamical, deterministic, probabilistic, and so on. And in no instance did we find a study that indicated that PMP bounds would be going down. So there's a wide range here, again, really reflecting the wide range in methods of how folks have looked at this. But there are studies that try and quantify this. So we also surveyed how other dam safety agencies, federal agencies, and so on currently deal with PMP and climate change. And I don't think that there's any one agency that we would point to say, like, they've got it, everybody should fall in line and follow suit. But everybody is, most large agencies are moving toward incorporating climate change or encouraging its qualitative incorporation in some way, shape, or form. So we concluded our volume essentially by recommending that PMP be implemented in the Colorado-New Mexico study, and it be done using the relationship in which we have the most confidence in the science and the state of the science, and that is the increase in precipitable water, or the increase in moisture holding capacity of the atmosphere as the climate warms. So we made three, again, fairly broad brush, but three recommendations of ways that this could be approached. And I'll walk you through them pretty quickly, because I think we want to hear from Bill how this may play out in actuality. So the first thing that we said is that you could take basically the way everything is done now and give it a qualitative nudge. And basically, when you have a range, like in the Colorado, New Mexico study, you had different people approaching the problem from different angles and different methods. So you're going to end up with a range of possible answers for PMP. And so you could say, well, all of these numbers were calculated without climate change incorporated. So where you can choose the higher one, go with that, because you didn't have climate change on the table. So just be more conservative in how you proceed. So that's the very qualitative way that one might consider this. The second approach is a more quantitative method, again, starting from the mostly deterministic ways that PMP is calculated now, and just saying that, okay, the PMP that you're going for that incorporates some signature of climate change would be the one that you're starting with, multiplied by a ratio of the maximum amount of moisture the atmosphere can hold in the future, a ratio between that and what you think the maximum amount of moisture we can hold now. And obviously there's a lot of details in how that would be done, but that was essentially the second recommendation. And then finally, the third way, and this sort of points to how different agencies are starting to move out of a purely deterministic mode and into a more risk-based probabilistic mode, is to look at how climate change might be incorporated in more of a precipitation frequency or just more comprehensive risk-based method. And to be honest, kind of punted a little bit on this one, only because this is, there's a wider range of possibilities in how this would be done, and there are a number of ongoing studies that may end up being really helpful leaders in the field, and they are yet to be complete. So a lot of this would be done under fairly complex statistical methods of incorporating frequency changes going forward. So in our volume, in our document, we point to a number of these studies, but for now, I will leave it at those were our recommendations, our main findings, and so we turned that back to the project sponsors, and I'll let Bill finish up with what they're doing.
Thanks, Kelly. And like Kelly said, we had 3 recommendations to consider. The qualitative one, in designing spillways for dams, we have to balance conservatism with economics, and so we can't have spillways that are just too costly to build. So we wanted to be careful with the conservatism. So going out of more conservatism as an approach. We're already pretty conservative. We're already looking at extreme storms, so we really didn't feel that was the best way to go. On the probabilistic side, a state regulatory agency, the way we manage our program is different than the way dam owner agencies like the Bureau and the Corps can manage their programs and make decisions. And we just don't, we don't use the probabilistic risk-based methods currently. And so we really struggled with how we might do that if we decided to go that way. So we fell back on the quantitative, more standards-based approach. And I'll just describe, what we arrived at there for our new rules. So it all keys into, like Kelly and Jeff and others have said, to this increase in temperature. And on the upper left is the existing data. This is the observed data that, like we've talked about this morning, shows increase in temperature over the last 30 years. And on the right is our representative concentration pathways, these global climate model projections, which show a likely increase of 2 degrees over the next 50 years. So we picked this 2020 to 2070 period represents the life of a designed engineered structure. So we thought that was appropriate to use in our thinking. Like we've talked about, the deterministic approach to PMP, it already maximizes the moisture. That's in the process. So if we think that the moisture is going to increase in the future, then it's a valid thing for us to use that relationship and in that methodology. And the way PMP is done now, we take a storm that already occurred and we look at it in our analysis. So that's one way we could go, is just wait for the next storm to happen and then redo our analysis. But our question was, what if the next storm happens is higher due to climate change, and we miss that? It already exceeds what the current capacity was. So we didn't want to do that either. We have this relationship that we've talked about, and simplistically put, warm air holds more water. We talked about a 1 degree increase in temperature leads roughly to a 3.5% increase in water holding capacity. So 2 degrees would give us 7% increase. And then for us, the question becomes, we really need to know, do we think the storm environment's going to be more favorable over these next 50 years to do that, for that to be the case? And we'll talk more about this in our talk this afternoon, but our program is looking more at potential failure mode analysis, which relies on the likelihood of an event occurring and our confidence in the science that leads us to that likelihood. So I asked Jeff and Kelly to put their thoughts on this increase in temperature and increase in moisture availability in that context. Give me the words to use for our analysis. So they came back and said they think the temperature increase, it's a very high likelihood, and they have strong confidence. There isn't a new study that's coming out there that's going to change their answer to that question. And then similarly with the precipitable water increase, They have a very high likelihood if a temperature goes up, it does increase the moisture capacity, and they have strong confidence in that as well. And we have some tools that we use in dam safety currently that help us decide what actions to take, if we're in the certain likelihood and confidence ranges. And this is our guidance document that we use for these failure modes. So in this case, it's a failure mode that's going to lead to an overtopping of a dam, which is a big concern for us. So at the top is the very high likelihood, encircled here there's direct evidence or substantial indirect evidence that suggests it is occurring or is likely to occur. So that's any failure mode. In this case, are we going to have increased moisture in our storm? So as we've said, we have a high likelihood for that. We have strong confidence in that, and these are our actions. So if we had a failure mode that we were worried about it at a dam, for some other failure mode, we would look at immediate draining of the reservoir under our statutory authority. We'd look at emergency actions to avoid failure. We'd expedite investigations that are designed to correct the situation, or we'd tell the dam owner that they had to do a zero storage until they could fix the situation. So these are our normal actions that these likelihoods and confidence lead us to. So with that, we really thought the science is leading us to this high likelihood with strong confidence that these extreme storms could potentially be worse, and we needed to incorporate that into our new proposed rules, which we're just starting to get out into the public now. So this is the rule that includes climate change. It's called this atmospheric moisture factor. Like Kelly said, our current process is kind of an ingredients-based, so this is another factor that we add to some other ones that are already in the process. And basically what it says is all rainfall depths, estimates calculated by means acceptable to the state engineer shall be multiplied by a factor of 1.07 to calculate runoff to account for expected increases in temperature and associated increases in atmospheric moisture over the 50-year period 2020 to 2070. So this is what we're proposing. We'll talk more about this and some of the other rule updates in our talk this afternoon. We still have to take this out to the general public, to take it around to the dam owners and engineering community in the state. So we'll see after all that process, and then we get into the formal rulemaking process. We'll see how this all turns out. But we really feel that there's scientific validation for this. We don't want to get caught flat-footed or on our heels if we have a new storm that happens that's impacted by this. So we really want to include this to keep the safest dams possible. So with that, I'll take any questions.
Thank you both. The climate scenarios threaten dams, as you discussed, but those also have risk factors for every other element of our infrastructure, such that the RPC 8 is, or 8.5 is a real societal threat, not just a water-related threat. How do we avoid that scenario? Question mark.
I'm going to turn that over to Kelly, or
I'm going to turn that over to Taryn or somebody. I mean, yeah, that's
I can
that's
take a
much
stab at
broader
it.
societal question.
So as a whole, the state's looking at how to integrate climate change projections into pretty much all that we do. I work a lot across agencies at different components of that, from transportation to energy to public health to agriculture. The infrastructure challenge is a really big one. I think what's so awesome about this study is that it's really one of the first where we're taking those climate projections and applying it to infrastructure so that we improve our the health and human safety of our population. There's work being done kind of with stormwater drainage and culverts and things like that that incorporate climate change. The challenge is, there's a long lifespan of all these infrastructure projects, and it's only really now that we're getting the momentum to integrate that. So there's a lot that's already been built that hasn't factored in those climate change components into it. So we're trying to improve it. We're trying to encourage folks to integrate climate change projections into those infrastructure builds or when they're going in and doing repairs, but we still have a long way to go. Other questions?
Thank you very much. And when you talk about precipitation events and the warming that we're seeing, is that changing the type of precipitation that we're seeing? Is it flashier? Are we getting less snowpack and more precipitation events in the form of rain? And how do you plan for that in relationship to a dam?
You know, that was one of the neat things about our study is it really looked at how it rained. So both parts of our study, the deterministic and the probabilistic, broke it down into they call it the storm types. So our analysis looks at the worst case scenario for a 2-hour thunderstorm, which is just solely a convective event. It looks at a 6-hour event that is, it's called a mesoscale, a larger event with embedded convection, so it could have thunderstorms within it. And then it looks at a longer scale, mid-latitude cyclone, a 2-day to 3-day event like the September 13 event. So for our storm analysis, we have the engineers run each scenario, and depending on the reservoir area and the configuration of the dam, we determine which of those scenarios is most critical to that infrastructure. You know, smaller reservoirs with less routing capacity are more susceptible to those really flashy 2-hour events. Bigger reservoirs with more routing they're influenced more by the long-term events. So we do the analysis to see which one controls the design of the spillway.
I would just add, in terms of the climate projections on the nature of flood-producing systems, broader scale events like the September 2013 flood, something like that might be something we can glean from current climate projections. But the real classic case of Colorado warm season, convective scale flash floods, those are still out in, those are not going to be captured by our current set of climate projections. So to estimate potential changes in those kinds of events, we're still really drawing on what we know about the ingredients and not necessarily able to say how that's going to be borne out because they're just so small scale.
Going back to my earlier question about wintertime cloud seeding, my simplistic conclusion from what you've said is that we should be able to get much more and much better guidance about when to attack a storm and do the cloud seeding. Would that be correct or not? Or am I, as usual, off into some remote corner?
That would speak to seasonality, which our study looked at. I don't think our study would really speak to that question specifically.
Do we have time for 2 more, Lorna?
Yeah, okay. More questions. Great. With the climate model specifically, have you
Can you hold the mic up a little higher?
Sorry. Have you considered looking at things basin by basin? Because with the downscaling of the future.
We can't hear you up here. I don't know if that mic is
Really close? Okay, sorry. Have you considered a basin by basin approach instead of just a flat factor or something like that? Because with the future climate projections, the trouble is the downscaling. So mountains are greatly different in the future climates than like plains region as a potential alternative or option.
Yeah, so I think the question is, did you consider developing different factors for different basins or for different elevations within basins?
And she said also something about downscaling of the climate model. So, our study was a regional study, so we looked at storms and gauged and weather station data, in all places in the state, both low elevation, high elevation. So our study was already pretty site-specific to Colorado and New Mexico. So I think we avoided some of those global climate model scale issues by doing that. And then we used the dynamic weather model results and some of the relationships that came out of that fill in gaps that we had, data gaps within those high elevation areas and basins where it hasn't rained hard before or there aren't weather stations. So I think our study was pretty comfortable that we did address those local variations that are specific to Colorado and New Mexico.
Yeah, and just to echo that, or repeat that PMP is a really unique beast. I've spent years trying to wrap my head around it, and I still, don't pretend to understand all of it. But it has a number of things going for it in terms of being able to simplify a really complex problem. So just to your point, if you were to come to the table and just say, how's climate change going to affect extreme precipitation in Colorado? Absolutely, you would never want a blanket approach. We have so many local complexities. So I think PMP, by virtue of its recipe and how it breaks things down into ingredients, and then the way in which it's calculated in very localized manners, it makes it more appropriate than in most applications to apply a ratio, because you're just multiplying whatever it started with those local effects. So anyway, just wanted to point out that this is very specific to a PMP application.
I was just wondering if you had estimated the increased cost of dams and spillways and that kind of thing. And then also, I've seen or read some papers about that actually there may be a global cooling because of things that are happening with the sun. I don't know anything about that, but is there a possibility that the temperature will level off or maybe even go down?
Yeah, we can work in reverse. I would love to tell you that there's any robust science pointing to a potential global cooling, and unfortunately, even though we have plenty of overlaying natural cycles in our atmosphere, both due to processes on Earth and within our relationship of the climate of the solar system, no, unfortunately, as Jeff and others have shown, the fact that we're operating in CO2 and greenhouse gas no man's land, we're at the point of just trumping all of those potentially compensating effects.
All right, well, thank you so much. Let's go ahead and thank our speakers. This was a fantastic session.